Well, hello everyone. Sorry for the delay. It seems like some things haven't changed between the pandemics, like the Mac users are still annoying everyone with their non-compatible laptops. So let's get started to this talk. We'll talk about White Rabbits, Flamingo, and also, best architecture practices, and how isolating your inputs-outputs can help you create a more sustainable, robust, and easily to maintain code base. Is this working? No. Okay, this is working. So a few words about me. I'm Sarah Diot-Girard. I've been working in machine learning and data science for almost 10 years now. I'm currently working at Hokodo, and if I was to be a bit tongue-in-cheek, I would say my job is trying to deploy machine learning models into production. That's not to say that everything that happened before is easy or not important, but I consider that really the end goal is to have something deployed in production so you can make an impact on the real world. I have a GitHub if you want to join me. And before we start, very small disclaimer. So this talk might or might not be very loosely inspired by Alice's Adventure in Wonderland. But yeah, my deepest apologies to all Lewis Carroll's fans in the audience if I've misconstrued your favorite character or something. So let's start with a little story. It might seem familiar to some of you. It was supposed to be like this really easy thing you wanted to fix, and then you ended up spending most of the time trying to do it because you make a small change here, things breaks on the other side, and then again, and every time you run your test suite, it runs forever. And so it's the end of the day, you're getting tired, your test suite has been running for maybe, I don't know, 24, 25, 26 minutes. And yeah, maybe you're dozing off a little bit, feeling very sleepy. And suddenly you jerk away, you're really sure you've seen something out of your corner of your eyes. You look, and what do you see? A little rabbit. How is it possible? So you're intrigued, you follow the little mammal, say okay, and you feel that the ground is disappearing under you and you are falling and falling into the rabbit hole. And yeah, you're like, okay, so this is a time for deep introspection, when you're falling in a rabbit hole at the end of a hard day of work. And so you're thinking, okay, how does this all started? So this started with this kind of innocuous-looking little script. So what does it do? At first, well, you are loading stuff, pandas.read.csv. I'm pretty sure everyone is familiar with that. You're isolating like the features and the labels. Then you want to scale your feature because, badly conditioned matrix, they can make numeric solver very slow, so you don't want that. You're training a classifier as a logistic regression, could be something else. And then you want to evaluate how well you did by computing the confusion matrix. So it seems pretty innocuous, and it was working fine. But then you say, okay, I want to make it more repeatable. I want to be able to extend that in the future, so I want to package that a little bit. So let's just write a couple of functions to try to make that more sustainable in the future. So you're going to write 3 functions for each step. So one for the standardization step. You say, okay, my data are here in this input file. I'm going to load it, scale it, save a parameter, and all is good. And you do the same thing for the training part and the evaluation part. So I don't know if the code is really readable at the end of the room, but basically it's just, instantiate a classifier, fit it, return it, dump it to the hard disk, and same evaluate, take all the things, compute the confusion matrix, print it. And if we go to have the equivalent of your script before, you write a main function to link them all together. And so this link function is just like, okay, I've got one step, it's standardizing my data, that's the pre-processing step. I've got a training step, and I've got an evaluation step. So seeing that it's all good, each function is doing one thing, very clean, very readable code. Yeah, there is one tiny problem here, most especially in these two lines. So this function, the standardized function, is doing IOs. So you read input at the beginning and you dump output, so the parameters of your standardization scalar at the end. And IOs in function make functions harder to test, and tests run slower. Why is that? Well, for the one thing, if you want to test a couple cases, or maybe more, because you've got some edge cases, every time you're going to have to create another CSV file. So it makes your test less readable, because you have to have both the test and the CSV file open to understand what's happening. And it's also a bit tedious, and then all of this multi-CSV file adding up in your GitHub repository, they'll end up being quite a large chunk of memory, and so it makes all of your repos so lower, and so on and so on. Because you've got output, it means that you have to have, after each unit test, some tear down step, removing all of your output to ensure that you're not leaving anything on the hard drive after you run your test. And because of all of that, it's kind of easy to break the test isolation principle. So that's the idea that each test should run the same if you run only one of it, or if you run the whole test suite. It's very easy to have one test dumping things in a file, and like you forgot to tear down properly, or there was like the test failed and the tear down step did not execute. And then it's going to interfere with the input of another test. So it's very easy to get flaky test suites. And also, because you keep doing calls to your hard drive, it makes your whole test list slower. And if you have a lot of unit tests like that, it adds up, and you ended up with this like 25 minutes test suite we had at the beginning. So yeah, that might be part of your problem. You're thinking as you are falling down this hole. Maybe that's why this small easy fix took me all day. Well, as you are musing about that, you finally reach the bottom of the hole, and here you find a small table. There is a bottle on the table. The bottle has a label. The label says, okay, drink me, and you'll learn everything about, back. You'll learn everything about pure functions. So you're like, okay, you know, it's a very long day. I would rather have a beer than this weird awareness drink, but you know, you take what you have. You kind of drink a large gulp out of it. And things start spinning again, like everything is growing bigger, or maybe you're growing smaller, but at the same time, you start learning things about what pure functions are. So what are pure functions? So pure functions are functions in a mathematical sense. So not in a, they are programming concept, but they have the same definition as a mathematical function. That is to say, the output is deterministically dependent only on the input. So this characteristic is really comes with like great properties. They are really easy to unit test, because every time you give a certain input to a function, it will spit out the same output. So it's easy to test all of your edge cases. Because of that, they're also really great if you ever need to parallelize anything. By design, you cannot have anything like rest condition if you are only using pure functions, so that means you basically get parallelization for free. They got a small caveat. There is no side effect. So that means you cannot have any state in this function. But you're thinking, okay, if I've got like this lightning fast test suite with a very good coverage and very robust code base, because I've got very high coverage, and if I ever need parallelization, I can get it for free. Okay, I'm okay with not having any side effects. But then, under the table, yeah, because you definitely grew tiny, and not the table grew bigger. But under the table, you find this small cake, and it says, it's me. And on the other side of it, you say, okay, all IOs, so all input outputs are side effects. And then you're like, huh, that's a problem. Because I want my code to actually do things. So that means I need to get data from a hard drive or for an external API, I need to get data in. And once I've computed something, I need to be able to save my model somewhere. I need to be able to return prediction to the database. So I need to make, to make a lot of IOs, so inputs and outputs, in order for my code to do anything. So you're like wondering, how can we have both the advantages of using pure functions, and still like do stuff in the real world? So you're thinking about that. You see this tiny little door, like, okay, let's proceed forward, and maybe a quick walk will help me clear my mind and find ideas. And on the other side of the door, you find a very friendly caterpillar who's like, oh, you seem worried. What are you worrying about? So you explain to the caterpillar, yeah, you know, I would like to use pure functions, but I also want my code to be able to do things with inputs, outputs, like put things on the hard drive, read from external APIs. And the caterpillar says, oh, maybe have you heard about the onion architecture? So onions for computer scientists, they are like trees for computer scientists, that is to say, quite simplistic, they've got 2 layers. This goes. And so the idea is that you'll put all of your IOs as far up, high on the abstraction, on the code base as possible. So it's going to be like the first thing you do and the last thing you do in your code is the outer layer of your code base. And all of the stuff, all the code that's actually the computations, that's all your business logic, all the things you really care about and want to have thoroughly unit tested, it's going to be into this functional core. So all of that is going to be pure function. Let's see an example. So I've taken, again, the same 3 things we've seen from the initial script. I've got standardized data here. And now it's rewritten as a pure function. So I take some data frame, pandas data frame, already instantiated. I create a scalar from scikit-learn's library, and I will fit the scalar, and I will return the parameters of the scalar and the scale data. And as you see, given that the scalar is deterministic, every time I give the same input, I'll get the same output, and I've got no side effects. We can do the same for the training part. I'm giving some data already preprocessed, labels. I'm instantiating a scikit-learn object again. Logistic regression is deterministic. If I were to use something which is not, like anything using gradient descent, I will have to set the random seed to ensure that the output is deterministic. And then I can fit my classifier of this object and return it. And same for the evaluation part. And now you say, okay, that's all good. I'm only acting on objects in memory, but how does all this thing get into the memory? That's what we are doing with our main, which is our outer layer we were talking about. So main is going to do some input, so load all of the CSV datasets into pandas data frame. It's also going to load, it can load like binary files, like so the pickle of a model, and the scaling part, the preprocessing part, if we want to do the evaluation separately from the script. And then the main is also responsible for the outputs. So when I get the preprocessing parameters, I save them to a CSV file. When I save the model, also it's responsible for printing the confusion matrix. So printing things to std out is also an output. It's also a side effect. And yeah, so say, okay, that's really good, but there are 2 things you haven't talked about, this load data and load scalar function. Aren't they doing some inputs? And the answer is yes, they are doing some inputs, IOs. So the load data is just like wrapper around read CSV and like basically tuple unpacking to split between labels and the rest of the columns. And as you can see, this function is mostly boilerplate code. So you want to package that because you don't want to repeat yourself everywhere in the code. But I mean, you trust pandas to be fairly unit tested, so you don't have to write so much unit tests for this code. You just can write some integration tests once to check that it passes through, but you don't have to have a lot of text on that. And load scalar is a bit longer, but it's still mostly just unpacking values and like storing them into this standard scalar object. So it's not doing any actual computation. Again, it's just boilerplate code. And if we go back to our initial diagrams, so we've got the main function, which is in the imperative outer shell, and the load data and load scalar, which are two helper functions, not doing any kind of actual computation. And all the things we really care about, which is how we standardize, and that can be, again, more pre-processing of the data, what kind of algorithm do we train on that, and how do we evaluate that. This is encoded as pure functions. So this I can unit test as much as I want very easily. Oh, well, that's great. So now you're pretty confident that this is going to help you with your current code base. And so you thank a lot the Caterpillar for its help. And you're like, OK, sure, let's start improving all of that with this onion architecture principle. That's until you get to this point, which is a bit like a matchy party, and you're like, OK, I've got this piece of code, and I'm really not sure that fitting it into the onion architecture is the right thing to do, or maybe not the only thing to do, because it's a bit weird. What are we talking about? Now, instead of printing the confusion matrix to the std out, you want to do something a bit more involved. You want to save it into a Google spreadsheet to be able to share it with other people in your team. And what's more, you've been evaluating on very big data sets, so you are spreading the load over several instances, and so you need to be able to get the current, the current content of the confusion matrix, and like add the new data point you have to it so that you get the new confusion matrix. So confusion matrix is basically the thing computing, you've got false positive and true positive, false negative and true negative, so you can just add them if you've got several batches of data and get the global thing out of it. So you can see there in this function, you've got some things which are around authentications to be able to access the Google API. Then you are basically opening a spreadsheet, then a given tab in this spreadsheet, and then you are doing what you actually care about, that is to say, getting the current state of the confusion matrix, updating it. So here our computation is an addition. You can imagine it's like a 200 lines function instead. And then we are basically dumping the new content into the same worksheet, so in the same tab of a spreadsheet. Okay, so this is the function doing a lot of IOs. Let's try to put it into an onion architecture style of coding. So at first, we're going to extract the functional core. So here it's very short. So once again, it's just additioning two confusion matrices. So, okay, we'll not talk more about that. The interesting part is the other part, which is, okay, the loading and then the saving part of these confusion matrices. Matrix, sorry. And you can see at first that, well, there are a lot of code repeating itself in the two functions. And the only really thing differing is the last line. In one case, you do a worksheet.get. In another case, you do a worksheet.update. But OK, let's, for now, there is this rule, like if you're repeating yourself twice, it's probably OK. If you're repeating yourself 3 times, you need to factorize it. So OK, it's only 2 times, we're probably fine. And yeah, and so now our main function is looking like that. So you load the confusion matrix, update it, save it. Good, that's onion architecture. This is a pure function, I can unit test. This is boilerplate code. I don't need to unit test, I will just test it with integration test. All good. Yeah. Sorry, I forgot I had that. Okay. Let's have a deeper look about the loading function. So there are a lot of things here which feels like, you know, you don't really care about that. There are things that are required by these JSpread third-party libraries to interact with Google API, but you, like, it really feels like if your own code is deeply intertwined with this JSpread third-party library. And it kind of feels a bit clunky because, well, for one thing, when you are testing, you probably don't want to have to set up credentials to access Google API every time. There are, you know, things around rate limiting. You don't want to access that again and again. So you're probably gonna end up using like something like mock, but mock can get really, really messy. Mock, they are hard to write, they are hard to read, they are harder to maintain. So, you know, I'm not a big proponent of mock, so I try to use them as little as possible. So this is kind of, I don't really like that. And also, if like the JSpread library is changing its API at some point in time, then you'll have to rewrite all of your code because it's so deeply intertwined with the JSpread API. It's going to make it hard to understand why are you impacted by this change. So it makes updating third-party libraries complex. So, you know, we can probably do better. So again, we're back to this thing. And what we really care about is this line, like I want to get the data which is in the B2 D4 area. I don't want anything else. So, okay, let's extract that, put it into its own little function. And same thing here. Okay, when we are saving, we are just updating. And this is our new main. So we are loading, updating, saving, same as before, except is it really the same as before? So instead of taking the name, I'm sorry, red and black is really not readable, but instead of taking the name of the worksheet we want to open, we are actually now taking a worksheet object directly. And this worksheet object is created by this open JWorksheet function. And this function is taking care of all of the authorization shenanigans and the details on how the JSpread library is really working. So if JSpread was to make any changes in the future, you only have to change this function about how authorization work or so. So it's better. And so again, this is flickering. Okay. So it's blinking. You see, when you are testing, the only thing you need to do is, you don't have to use actual mocks. You can do with having some, you know, test double, so just create an object and you say, okay, it has to implement a get and an update method, and then it will be better. So it's an improvement, and it's called, is this doing the same thing again? Yes. Do I get to restart it? Yeah, okay. Can I get my speaker note again or not? Just try that. And I lost the other one. Yep. So this is the principle. It's called dependency injection. So the idea is that your code should not be responsible for instantiating any of the third parties object you are using. it should receive it from the outside. So here it receives it receives from the main. This OpenJ worksheet is responsible for creating the worksheet object and giving it to your other functions. So it's already much better for testing and also like for robustness to future change due to third parties API. There's still something a bit bothering me though. It's this area parameter. It's kind of oddly specific to what you are doing with Google APIs. It wouldn't make any sense if you were using, for example, a local CSV or something. And so we can take this dependency injection one step further and try to do something which is using abstraction layer. So abstraction layer will define a contract of what you will expect from the outside world. And then you'll get an object which is instantiated to respect that contract. So in this ID, what we want is basically we want a spreadsheet or worksheet object, and it has to have two things. We want to be able to load data out of it, and we want to be able to dump data in it. And so I could write it like that. So this is a spreadsheet object. And so you see that in the init, I had all of the authentication shenanigans I had before, and also this self.area principle. So all the shenanigans I had before. I have the things like around how do I open a given tab, which can change in the future, but I'll just have to change it here. And there is this area attribute, which is used only by this type of spreadsheet. And then my load and my dump are, again, they basically take, they return a numpy array for the load, and they take a numpy array for the dump, and they save it, and they do all that they need to do to get it saved in the spreadsheet. And yeah, so it might be a bit confusing, but the exact difference between just dependency injection and using abstraction layer is in dependency injection, our load and save confusion matrix functions, they are dependent on the things which are required by the third-party API. Here it needs an area of data to load or to where to dump to. Here I just have a load and dump, and it's really agnostic to my third-party dependencies. And so if I want to use something else than Google API, so maybe I want to use store things in the spreadsheet only in production, but when I am developing, I just want to store it to a local Excel file. Or maybe I want to use a local Excel file when I'm doing some local test, you know, and I don't want to instantiate all of these authorization clients during testing. And so I can just write another function. So it's this Excel spreadsheet. And so you see that the init is very different. And also there are the load and the dump function are not the same, but they are also returning an NP array, so using pandas Redis Excel and then using dot values to get the NP arrays out of it. And on the other hand, they are taking also NP arrays and instantiating a data frame to use, again, the pandas capabilities to work with Excel. But all of this, your end user, or that is to say, you not writing the IOs, your coworkers, or the future you in 2 months, they don't care about these details. They just say, okay, I can load and dump things into an Excel file. So how can we show that both of these classes we developed are actually the same, implementing the same abstraction? They are the same API. So the object-oriented language typically use class inheritance to do that. So we'll have an abstract class, we'll have just a load and a dump method and say, okay, raise not implemented error in here, and so you'll have to subclass this abstract class to get it working. There's actually a better way of doing that in Python that is more respectful of what we call duck typing. So the idea of duck typing, if it quacks like a duck, and if it swims like a duck, and if it walks like a duck, then it's a duck. That's the idea that if you've got any object you can iterate upon, so any object instantiating the dunder iter function, you don't have to have it explicitly subclass the iterable abstract class. And so since Python 3.8, and before if you are using MyPy, you can use something called protocol, which is saying, okay, my load function returns an NP array, my dump function takes an NP array, and basically my main function, you have to have managed to instantiate a spreadsheet at some point to make it work. Good. So you're, okay, maybe a bit overwhelmed by all of this information, but you're nibbling your scone, you know, you are sitting for tea, grabbing a teapot to get, and then in the teapot, what do you have? A little dorm house, and you say, okay, that's really cool, but you know, remember that using the bad abstraction, it's really, really costly. So in this very simple cases, load dump, it's kind of easy to see what the right abstraction is, but in some other cases, it can be much harder. So it's already worth taking quite a lot of time to determine if the abstraction is the right one. When you find the right one, it should feel quite intuitive in a sense. And yeah, there is this thing around the Zen of Python, which say if the implementation is easy to explain, it's maybe a good idea. So there's this idea that it should be kind of natural that this is the right abstraction to use. Okay, now let's go to a party of the Queen Croquet after the tea party. And I don't know if you know, but Queen Croquet is played with flamingo and hedgehogs, and so that's kind of how it feels when you get to some other more complex code architectural needs, when things are like really not behaving the way they should. So quite quickly, because we're a bit short on time, the idea we had so far was basically load, do stuff, and dump. And with the do stuff part, not including any IOs. But in real life, you've got things like, you've got a long computation and you want to be able to get regular logging things on what's happening. Or you're doing a very long training and you want to be able to save checkpoints to restart your training in the middle if anything goes bad. Or you have got in a workflow, and for example, you are caching this very long computation, so you have to access the DB to know how long ago this computation was made before deciding if you want to make it or not. So these are things happening. It's worth mentioning that as much as possible, you should try to stick to this initial load, do, dump structure as long as you can, so as long as you don't have any major performance issues or cost issues, because it's really, really easier. But when it does not work, we can have a look at how Python is doing it with the implementation of logging in the standard library. And so a logger is basically something which is taking as input a string, and it's responsible for doing something with a string. So it might display it in debug mode and not display it in production environment and so on. And so the logger is from the standard library, so it knows nothing about your own application code. And your application is just sending things to the logger, and it does not rely on the logger to do anything for it afterwards. And so you should try to have the same idea when you have like saving checkpoints in training or something. Create something which behaves like a logger. It should be agnostic to what your application is actually doing, and your application should not be dependent on it. Yes, so it looks like you're winning this game of croquet, and the Queen of Hearts is getting very annoyed with that. And so she's screaming, "Oh, fair and you're like, okay, this is not going good. And you start running because you're feeling very afraid. And you remind all the things you've learned into this wonderland. One thing is, sorry, I'm going to skip that. One thing is that IOs should occur at the highest level possible. So first thing and last thing in your code. Then you should try to inject dependencies so that your code is agnostic to third-party dependencies, and try to use abstraction layer. But the most important thing of all is, as the Zen of Python is saying, practicality beats purity. Well, suddenly you jerk awake and you're like, okay, I'm probably going to be able to merge these merge requests. I'm almost not late at all. And then, okay, you definitely forgot to commit before push forcing again. Wow. I think there won't be any time for questions. I just wanted to give a quick shout out to my coworker, Sophie, who made the wonderful illustration, and Joachim, who helped me with the nitty-gritty details of the CSS. And I'll be taking any question outside, I guess.